Welcome back. We're live at the Glenn Gerberg Weather and Climate Summit here in Breckenridge, Colorado. Beautiful sunny day today. Cold, not as cold as it was yesterday, but just a beautiful day, especially with the Uller Parade yesterday that went on. I did have one quick announcement before I introduce Jim White. If we take a look at the website, we did make a few changes last night, or I should say enhancements, and that is when you go to the home page, you can now go over to videos as you have before if you wanted to see videos of the sessions. And what we're doing is we're editing and making sure that the sessions are complete sessions because we uploaded videos quickly the last few days to get to the YouTube channel. And that meant that you got everything. So you got 30 minutes of the full screen billboard of the agenda and all that sort of stuff. So we have day one fully completed. So you can see Paul Schlotter's and Don Burgess's presentation along with the Q&A session. And so if you keep checking back, we'll be updating that site throughout next week to make sure that the sessions are crisp and to the point. So with that, I'd like to introduce our final speaker for this Glenn Gerberg Weather and Climate Summit 2012. And it is, sometimes I like to say we save the best for last, but Jim has been with the summit for quite a long time. And he's a research professor at the University of Colorado, director of the Institute for Arctic and Alpine Research. And I'm just going to set up the PowerPoint here so he's all ready to go. Let's take a little video. Jim does some very exciting research in Greenland, and we've had the fortunate experience at Storm Center Communications to go with Jim and be in Greenland the last 3 years in a row. And we've had our crew up there. We had Dan Satterfield up there who did a number of stories at his station down in Huntsville, and that went over quite well. And we'll be doing some more stuff in the future as well. Also, the Weather Channel ran some pieces on the research being done in Greenland. So take a close look, turn up your speakers on your computer, and enjoy this introduction to Jim White.
What you see here is a piece of ice from the climate change between the last glacial and the present climate of the Holocene. It's about 11,000 years old, and it contains a lot of tiny little bubbles of the ancient atmosphere. When this ice is melting now, it turns into water, and it has never been water for 11,000 years. My first season was in 1980, 29 years ago. That was a marriage for life.
I feel a sense of awe when I am able to peer into the deep past time. It's really like pulling back the veil, and it's a very exciting feeling.
Airport is now the staging ground for an international effort to reconstruct climate history and learn more about global warming.
Gear 7-2, keep up speed during approach. Your number 1, I have traffic from behind. Gear 7-2.
Research that's being accomplished in these different camps in the Arctic. Then you look at the news headlines and you see that a whole lot of that research, specifically along the lines of global climate change, is being done here. We're the only unit in the world that flies the specialized C-130 on skis, which allows us to support the scientific efforts and take these large airplanes and land them on skis. to contribute to the nation.
It's a very simple life. It's kind of like a frontier outpost. We sleep mostly in those red structures. They're called weather ports. Usually there are 4 or 6 bunk beds to the weather port. It's always light. It takes a couple of nights to get used to it, but then you get so tired from work and from not sleeping the nights before that it no longer becomes a problem.
I work mostly as coordinator of the project, kind to get the drill teams and the scientists and the logistic people and the airplanes to come. But my main interest is really the ice cores. I normally find half a day to work every day, and then I go into the science trench and work with the ice cores.
You can hear the bubbles coming out of the ice. The ice now, it's about 3,000 years old.
NEAM is really trying to get a record of the last time that the Earth was warmer than today. So it's an analog for what our future looks like under global warming.
The ice drilling season runs from May through September, and this project will wrap in 2010 when scientists hope to hit bedrock.
Thank you very much. Thank you all of you for hanging in for the last day. That was a nice introduction. I think the NEAM Ice Core project is one of several that I've worked on in Greenland, and I'm also working in Antarctica. These are projects in which we try to look into the past, and the idea in looking in the past is to get an idea of how climate functions on timescales, what I say, timescales of human interest. That is 1, 2, 3, 5 years, 10 years, 20 years, that kind of time scale. And ice cores are kind of unique in that they can get that kind of time resolution, but go back 10, 20, 30,000 years. I am going to talk a little bit about ice cores today, but not a whole lot. I have the luxury of going last, and so I'm going to try to basically address some of the things that we've addressed during the week, take a look at those, give sort of my spin on it. If we have time, I'd like to get into some of the energy options we have for the future. I also teach a course on energy and energy impacts on the environment, and those impacts are all the way from climate, obviously, but also it's not all that well known, but given the huge amount of energy that we need, all energy types are going to have some impact. And so one of the ones that I thought would be interesting to look at was nuclear, in that at this conference we don't shy away from any of the most controversial topics that we have, and nuclear is indeed a controversial topic. Question is whether or not I will ramble on too long to even get to that point. I did want to tell you about, I think I have in the past shown you that sort of my favorite poster child for human impacts on the environment is a satellite composite put together by NOAA that shows the Earth at night. And I show that to my students, and I tell them, if you look at the Earth at night and you don't get the idea that human beings have a large impact on the planet, then you're sort of missing the boat. This is my new favorite one. These are all plane tracks that are been put together and put on a globe. And you can watch all the flights go back and forth.
Is that Eastern time? No, just it looks like it is.
Yeah, it's on the 8th. But you can see, for example, these are all, so this is, I believe, one day. I'd have to check on that. But you watch, this is North America waking up. And those are all airplanes. And it's just pretty, I think it's a very graphic and good way to get an idea of just how large we are on the planet. I'm going to stop this one and kill it because there's a different version of this, and I can give you the link to these. This is obviously a flat view, just showing a couple of things here. Notice, this is the larger emitter of carbon dioxide in the world over here, and a country that still, on average, people use somewhere in the neighborhood of 5 to 10 times less energy per capita than we do in Europe or in the United States. Plains here, but not nearly the bee's nest of activity that you see here. Same is true for India. And now compare that to what you see here when Europe begins to wake up. And compare that to what you see here when North America begins to wake up. Brazil is another country that is industrializing rapidly. As a matter of fact, one of the things we'll talk about today, and it was mentioned earlier, is that in 2011, we humans burned more fossil fuels than we have ever. So 2011 was yet another record year. And we know that this country and countries and this part of the world were suffering from an economic downturn at that time. It just shows you that when this part of the world and this part of the world really begins to enter into the same kind of energy consumption, the same kind of economy that we have in the industrialized world, the first world, if you will, that the energy challenge will be enormous. We're not talking about, we've talked about this before, we're not talking about a 5, 10, 15% increase in energy needs. We're talking about a 100%, 200%, 300%, 400% increase in energy needs. And one of the things that's important to recognize is that energy is only one of the, can you make that go away? Sure. Go away. And then you should click on the, oh, I do, yeah, click on it.
Jim, when you said 2011, we burned more fossil fuels, you mean for any given year, or 2011 was more than all the other years before?
No, 2011 for any given year. For any given year. I also want to point out, if you can play that again, this is a short version. You can get a longer version on the web, but we also put a camera down the Neem borehole. This is the bottom of the ice sheet. So this ice in here is in the neighborhood of 150 to 200,000 years old. And that chunk of rock down there, or that little pieces of rock and ice, haven't seen daylight for probably in the neighborhood of million, 2 million years, something like that. So one of the things that we're going to do at Neem this summer is to try to get down there and grab some rock. We've drilled a rock core out of there, but we weren't successful in terms of snapping it off and bringing it up to the surface. So that's something that we're going to be doing this summer at Neem. One of the interesting things we're doing at this conference this year is obviously we're streaming, so there's a lot larger audience than we have had in the past, and there are some new folks here. So I'm just going to take about 4 slides, my 4 favorite slides that I use whenever I talk about energy and climate change, and go through those. And those of you who've been to this conference before have seen them, so you can sort of tune out a little bit. But I think this is important because we tend to focus on the complexity of weather, and it is complex. And that is as you know, it's a challenge then to talk to people who are skeptical about climate change or who are curious about climate change. They tend to convolve weather and climate, and they don't see the difference very easily, and the difference is sometimes not so easily seen. One of the ways I like to get around that is to take a step back and say, let's look at the globe as an average. So the Pacific Decadal Oscillation just got averaged up, and the AO gets averaged up, and all the other oscillations get averaged up. So let's just look at the globe. And when you look at the globe, it's actually pretty interesting. The climate system is simple. And this is something I think everyone can grasp, that the climate system, when you look at the large scale, is pretty simple. It just depends on how much energy we get from the sun, how much of that energy is reflected back to outer space. So the white bits, the sea ice that Jennifer was just talking about, and the amount of greenhouse gas. That is the third important part of our climate system. All of these things can change. Our orbit around the Earth, our orbit around the sun changes. This is actually what paces the big glaciations that you see, the 100,000-year cycle of glaciations that we've seen over the last million years or so on the planet. The albedo obviously also changes. On short terms, the easiest one to see is when volcanoes go off. And you folks know that when volcanoes go off, you're going to see some cooler conditions for the next 2 or 3 years. It's how long it takes to wash the material out of the stratosphere. And greenhouse gases can also change. They change over time. They've changed on very long time scales because of the way the plates move around the planet, how much carbon is stored, primarily by carbonates, that is not available then to be in the atmosphere. Ocean circulation, we talked about this before, is a very big part of the carbon cycle. And this brings up an interesting question. Dale and I were sitting in an extraordinarily frozen hot tub the other day talking about, okay, you know, we burn these fossil fuels. If we stop burning fossil fuels, the CO2 will come out of the atmosphere and we'll get back to a cooler climate in a relatively quick period of time. And he said we wouldn't get back to the relatively quick. Anyway, it's important to recognize that there's a couple of different what we call residence times. There's a residence time for, or what we call lifetime. So a lifetime is simply how much material you have divided by the use rate. So if you've got a lot of material and the use rate is slow, then the lifetime is long. If you've got very little material and the use rate is high, then the lifetime is short. And if you just calculate what's the lifetime of carbon dioxide in the atmosphere, it's pretty short, because there's a certain amount of CO2 in the atmosphere, but the plants go through a lot of this every year, and the ocean goes through a lot of this every year. So it turns out that the simple lifetime of CO2 is only about 3 years. And I hear that back from people when I talk to them. Well, if the lifetime of CO2 in the atmosphere, how does it clean itself out? And the reason has to do with the fact that carbon dioxide interacts with the ocean. So it dissolves in the ocean, and it's not just going to stay there. As CO2, for example, if we begin to get really serious about fossil fuels and start to drop the amount of CO2 that we add to the atmosphere, CO2 might begin to drop a little bit, but the carbon that we've stored in the ocean, our bank, if you will, over the last 100 years starts to come back out. And that makes the effective lifetime, so that's the other type of lifetime, the effective lifetime of carbon in the atmosphere, hundreds, if not thousands of years. So it depends on the circulation of the ocean. But that's important to know, because what we're doing today in terms of adding greenhouse gases to the atmosphere is not going to go away in a short period of time. We're making a commitment in terms of CO2 in the atmosphere for at least hundreds, if not thousands of years. We have talked about this in the past. The only really way around that is to remove this stuff from the atmosphere ourselves. Talk more in the light. Okay. Go to the light. Go to the light. But I was always taught that if you went to the light, this was bad, right? You know, Jim, don't go to the light. All right. Just another way to scale this is, this is my third of my favorite slides. We know that we can calculate how much energy we get from the sun. We can measure how much energy we get from the sun. We know that that's not enough energy for us to be a liquid planet. We would be too cold. The average temperature of the planet without greenhouse gas, without an atmosphere, is about -18 degrees C. That's how far away we are from the sun. It's because of greenhouse gases that the average temperature of the planet is around +15 degrees Celsius. And so there's about a 60-degree Fahrenheit or 33-degree Celsius increase in the temperature of the planet because of greenhouse gases. And that's important to recognize again, because, I mean, if you think about it, if this is true, this is simple physics, if you add more greenhouse gases to the atmosphere, you're going to change climate. And there's going to be a lot of debate about how it happens locally and what happens in terms of all the internal oscillations and everything else that goes on. But in fact, you will change climate. And that's not something that we are allowed to deny. That's not something that we can argue about. That's not something we can pass a law and says, I'm sorry, but you know, the Earth is not going to warm up. This is physics, and you just don't get a choice. You know, it's sort of like gravity. I think I've made this example, I've given this example before, but as a matter of fact, we can do this. This is a wonderful thing here. Come here, Nancy. And grab your chair. Right, grab your chair. So this is an example I use in classes. Can you see her? So stand up on a chair.
Standing?
Yeah.
You're already tall enough.
All right. All right, so we can do a little thought exercise. All right. What happens if I push Nancy over? She'll fall off the chair. All right. Now, but let's get more specific. All right. We're the scientific part of what happens in the newsroom here. You know, if she puts her arm out, might it break at that height? Yeah. All right. So what if, turn around a little bit. What if I tie her hands behind her back and push her over? Might there be even more damage? Might this beautiful face, actually it might break her nose or something like that, or something worse. I've done this example in class for some 20 years. Right? Never once in 20 years has anyone suggested that she won't fall. And that, I think, is a powerful statement of how we understand physics. We understand that gravity is going to work no matter what. Off you go, my dear. Thank you very much.
You're very welcome.
The lovely Nancy Van Camp. We have the same, back to the light, Jim. We have the same situation with greenhouse gases. Carbon dioxide, methane, nitrous oxide are going to absorb energy emitted from the earth whether we like it or not. That is simple physics. That is going to happen. Right? You can't argue your way out of that. All right, so this is my fourth slide. Now I get into more what I want to talk about today. Is it surprising that human beings are changing the planet? I'm collecting sort of the interesting little factoids that scale human impact on the planet, and this is my current list right now. We're certainly altering the Earth's energy balance. We are changing climate. We move 10 times more dirt than all rivers and streams and atmospheric dust combined per year, with tractors and caterpillars and earth movers and all that kind of stuff. We make more fertilizer, nitrogen fertilizer. One of the basic ways in which our planet functions is that bacteria take nitrogen out of the atmosphere and their byproduct is ammonia and nitrate. Plants need that. Without plants, we don't have photosynthesis. Without photosynthesis, we don't have life, because that's those sugars made by sunlight, CO2, and nutrients is what drives all the rest of, basically, there's a small amount elsewhere, but basically all of the life that all the food that we have is driven by that. And we figured out how to make fertilizer back in the 1930s, got into it big time in the 1950s, and we passed bacteria in terms of being the #1 fertilizer producer sometime in the last 10 years or so. So we are big there. We make more sulfate, which is a cloud condensing nuclei, than all ocean phytoplankton, and our current energy needs, there's a number of ways you can say this, are currently equal to just about all the harvestable wind energy in the atmosphere. So this is important to recognize, because this is one of the things that we should get into in later conferences, is this whole issue of sustainability. We've got an enormous challenge ahead, and it's really not just a challenge for the planet, it's a challenge for us, because we are the major agent of change on the planet. And we are the only beast on the planet that I know of that can actually think about its position and potentially alter its position on the planet. Okay, so back to some few things I want to talk about today. I do want to talk about sea level estimates for the future. I did want to talk a little bit about permafrost and methane clathrates. These are carbon-bearing materials that we find in cold regions of the world. This is one of these things that we keep an eye on. We heard a little bit about this earlier this week. Is it a mega disaster? Is it just aliens? Not even going to go there. It was another record year for fossil fuel burning, another record year for CO2. Try to give you a little bit of the story behind the story there, and I already talked about Dale's question about the lifetime of greenhouse gases, so I will ignore that. Sea level estimates for the future. There's been a lot of work done recently on looking at potential, how rapidly sea level is going to rise. The latest Intergovernmental Panel on Climate Change report had a relatively, what's now we know is a relatively low number of about 40 centimeters, half meter, let's round these things off, by the year 2100. The people who wrote that knew that there were other feedbacks in the system that they were nervous about, and they actually put a whole lot of caveats in there to express that, but Since the last IPCC report, we now know that there are dynamic processes in ice sheets that we did not include in the last one. Those dynamical processes are things like warmer ocean currents coming in and warming the tongue of these large ice flows that come out of Greenland. Jakobshavn area, there's a bunch around all these major ice sheets. It's where ice tends to funnel in just like a river in the valleys and flow out in preferential places. And it's very important what happens in those preferential places, because if you have frozen ice on rock, it moves slowly. If you have some way in which warm water, for example, can come in and start melting that bottom off more quickly and even creep back in and lubricate, then things flow much, much faster. The same thing happens at the surface, where you have warming at the surface that creates melt ponds. And I know the guys who've gone to Greenland have seen these beautiful blue lake melt ponds around the ring of Greenland, around the edge of Greenland. These things can indeed melt their way down through the ice and, again, lubricate the base of the ice sheet and move ice much faster than we thought it could move before. This is recent research that has changed what we think is going to happen for the next X years. We always sort of scale to 2100 first. But we certainly think that now the rise rate is going to be somewhere in the neighborhood of a meter, 3 feet by 2100, and that's turning into a more conservative number. So it's 40 centimeters is still a lot of sea level rise by 2100. 3 feet is, and we'll show you some graphics to what that looks like, is a lot of sea level rise by 2100. I will take this a little bit further, because one of the problems we have is that 2100 is not the end of the world. I think 2012 is. Is that right? Yeah. Okay. December? Okay. So this would be the last talk ever given at the Weather Summit here at Breckenridge. Sorry about that, but we're not going out with a bang. Anyway, 2100 is not the end of the world. Sea level will continue to rise. And we know from looking at the history of the planet that it does take a while for big ice sheets to melt. And one of the interesting questions is just how high will this go? Is it another 10 feet? Is it another 20 feet? Is it 30 feet? These are the actual numbers are quite high. And it tells you something how dynamical our planet is when it comes to temperatures and when it comes to sea level. We don't know quite where it's going to settle, and in part that's because we don't know quite what we're going to do. Are we going to continue to burn fossil fuels? Are we going to raise CO2 levels to 5, 6, 7, or 1,000 parts per million? Or are we going to dial that back and do something different? What we do is going to have a big impact on how high sea level is going to go. But I'll give you an idea of what the past teaches us in terms of sea levels. West Antarctica is a new focus of attention. One of the things that we've seen in the Nîmes ice core is that and I'll show you a graphic of this in a moment, but the Greenland ice sheet, at least in the north, wasn't terribly different than it is today. And we know that from looking at the climate that we see in the ice core, if you look into the past, as you look at the last interglacial period, it was a little bit warmer there than it was today, but that's true pretty much all around the world. The last interglacial period was a few degrees warmer. Sea level was a few meters higher than today. That we see from a number of different proxies around the world. That area of Greenland doesn't look anomalous. And if you think about it, if the ice sheet was much, much lower, then that area of the world would look much, much warmer, because it's already at a couple kilometers elevation. It's like 10,000 feet or something like that. If that ice sheet was much smaller, down around, say, 5,000 feet, then just because as you go up in the atmosphere, it gets colder. I don't know if you guys knew that. But it would be there would be an amplification of warming that we would see in that ice core if indeed the ice sheet was much smaller. We don't see that amplification. That tells us that that area of Greenland, even though it was warmer, that area of Greenland was about as large, or the ice sheet was about as large as it is today. which focuses more of our attention then, because we know sea level was higher at the time. We can see beach remains, we can see corals. I'll show you a picture of corals in the Miami area that are meters higher than today, and so we know that sea level was higher. So where did that sea level come from? And our attention is going more and more towards West Antarctica. And I know that in this conference and in many places you'll talk about sea level. We hear a lot about Greenland, but really West Antarctica, I think, is going to become more and more the focus. As a matter of fact, we have yet to find last interglacial period ice in West Antarctica. And I'll show you what that may look like here in a moment in the graphic. The eventual height, as I said, is going to depend on greenhouse gas levels. But 60 feet or higher would seem quite possible, maybe in the next 1,000 years or something like that. That's a long time out. And we are very clever beasts, and we can do something about this in the meanwhile. But if we just left things to go, if we just let nature run its course, this would be roughly where we would go. Sort of a little graphic here of sea level rise from Greenland ice versus Greenland temperature, just showing you the time history of the estimates. This is higher sea level rise here. And what you see is that the estimates back in the 1960s, this is a box plot just showing you the range of sea level rise from the estimate and the time period over which the estimate was taken. So as you look into the past, we had much coarser time resolution to look at. During the satellite era, we start to get many, many more estimates, and they have much smaller time frames attached to them. But as you look into the past, the ice loss from Greenland back in the 60s, 70s, there's no, maybe a little bit going on here, but not a whole lot. But if you look at this, this is the recent estimates, and the recent estimates have been going up pretty much exponentially. And this is one of the reasons why the next IPCC report is going to have certainly a higher estimate for where we're going in terms of sea level contribution from Greenland. But we're now up into maybe 5, 6, 7 times higher estimates for ice loss from Greenland than we were thinking about even just about in the 1990s or so. Part of that may be real in that Greenland is indeed accelerating. Part of it may be a little bit better observations, but our best guess is that most of that is real. That's about 20 feet of sea level right there. Those words are actually sketched out on the Greenland ice sheet. Google Earth wipes them out every time because they don't believe that that's real. It's sort of like some long history of this sort of thing happening. Anyway, so this was sort of our thinking of what the ice sheet might look like. This is an article by Kurt Cuffey and some colleagues. Thickest parts here, the Neem ice core is up in this area in here. The idea was that the southern lobe of the ice sheet melted off and that this thinned up here. We now think that this stayed roughly at the amount of ice we had here, and while the southern lobe might have thinned quite a bit, this area appears to have been fed by probably maybe even some moisture off a less than ice covered Arctic and allowed to continue to grow. So we're still wondering how this can possibly be, but that's what the ice core evidence is showing us. And again, turning our attention to West Antarctica. And as you think about this and as viewers ask you questions, I think West Antarctica ought to be a point where you might want to focus attention. I'd point out just some anecdotal things that happened this summer up at Neem. Neem pointed right in here somewhere. It's been getting warmer and warmer at Neem. In part, I think, because of shifts in the AO, and in part, obviously, the baseline is ramping up as greenhouse gas levels go up in the atmosphere. We've gotten into the situation now where takeoffs and landings in those big C-130s that you saw in the video are getting harder and harder. Just like skiing, if the snow is really cold and powdery, it's really easy to glide downhill. When it gets wet and sticky, then you go more slowly. And these big airplanes have a lot of trouble taking off when the snow is wet and sticky. This summer we had a bunch of distinguished visitors, energy ministers. We had a king and a queen show up. We had a bunch of people. People love to come up to these ice camps. But they love to come for a few hours and take a look around. Guys in the back can attest to this. They've seen this. And we had one situation in which the plane couldn't get back off. And so this was, this actually causes some interesting problems in camp, because what do you do with all these distinguished visitors? They're not people who are going to go want to crawl off in one of the relatively primitive sleeping environments we have. You know, they require some maintenance. These are people that a little more high maintenance than your average person.
So what did you do?
We got them off. We had a night flight. The sun never really goes down in the summertime, obviously, but it drops lower on the horizon. Temperatures do cool off. So we loaded them up late at night. We also had something called jet-assisted takeoff, JATO, which is, if you guys ever get a chance to go up to Greenland, that's a thrill. Basically, they light rockets that are attached to the side of the airplane. And if that doesn't get you up in the air, then you're not going anywhere. You're not going anywhere. But it is making work on Greenland more challenging. One of the things that we would like to do is go down to this part of Greenland and drill another ice core. There's only been one drilled down here to try to determine whether or not there was any ice during the last interglacial period. How much of that ice loss really came from southern Greenland. And we're not 100% sure how we're going to pull that off, because the conditions down there are really tough when it comes to getting these big airplanes in and out. I'll also, I don't know if you know, if you remember there in the video, there's a big black dome. That dome is now on skis. So one of our thrilling things we did this summer was put it on a large, basically bicycle wheel turned on its side, and jacked it up and put it on skis. So we can now drag it all over Greenland wherever we want to. So it's the largest mobile home.
Does it have a NOAA weather radio on it?
Yeah.
It ought to. It really ought to. Yeah, there's you can see that dome is now on skis. Just want to point out, as I said before, West Antarctic ice sheet is become our new focus for where sea ice, or where sea level came from in the past, and therefore an area we want to take a much harder look at in terms of where sea level will come from in the future. This is a bedrock map of Antarctica, East Antarctica over here, West Antarctica over here, and you can see that the scale's kind of difficult to see, but there are deep ocean troughs in here, 10,000 foot depths in some of these areas. There's an archipelago that runs through here and an island mass out here, and these places probably always had ice during the last interglacial periods. You have to go back millions of years before Antarctica doesn't have ice on it. And I'll show you a time frame that actually we can pin that down a little bit better. So what may have happened in previous interglacials is the West Antarctic ice sheet, which today covers this whole area, might have been an ice cap along here and an ice cap here and sea ice in here, but this was not ice. Today this is well below, the base of the ice sheet's well below sea level. It's a very unstable ice sheet from the sense of sea level rise, from the sense of warming ocean, because this stuff can then come out a whole lot faster than ice that's loaded up on bedrock, which is most of East Antarctica. So this is not something that people don't normally download pictures of bedrock for Antarctica, so I think it's kind of important and kind of cool to note that the West Antarctic ice sheet is indeed mostly below sea level. The base of it is mostly below sea level. Okay, so what does 1 meter of sea level look like? Many coastal cities no longer function. This is the, we tend to look at sea level rises like, okay, you got salt water in your backyard. That's not a good thing, obviously. But things happen long before that. We heard earlier in the week that freshwater becomes an issue in Pacific Ocean islands, probably long before sea level is going to make these ocean islands uninhabitable. They will have lost their freshwater supplies, because as salt water rises, it pushes the freshwater lens out. That's true also in coastal cities. Coastal cities that rely on groundwater or rainwater that soaks into the ground to get their water supplies. We'll see more and more saltwater intrusion into their supplies. There are also a lot of infrastructure problems, and one of the things that I and other climate scientists have been doing recently is talking more to the managers of cities. I forgot who gave the example of the sewage treatment plant being put out in the bay, raising that, was that? Was in Boston, yeah. Raising it up 1.5 feet, great idea. I mean, you have to think ahead on things like that. But that is indeed, it's the infrastructure that really becomes problematic. Gas lines are typically buried. Some power lines are buried. As salt water pushes its way in, it compromises the integrity of these systems. As I mentioned, freshwater supplies, sewage systems. Sewage systems, almost all of them work on the concept of gravity, that when you flush, it flows downhill. And as sea level rises, downhill comes up to you. And it no longer functions very well. Interesting, it functions well for the folks up in the 15th floor of the penthouse, but you know, the poor schmuck down on the first floor. Storm drainage systems, etc. These are basic, you know, infrastructure of cities that becomes becomes basically dysfunctional as sea level rise. And people miss this. This is really it's the city planners that I think are more interested and more worried about sea level rise and climate change than many of the folks on city council and people like that who may have other political ideas. I think I showed this to you last year. This is Miami with 3 feet of sea level rise. You see Miami Beach out here is underwater. Miami Airport becomes a seaport. Yes, you can actually, might be able to set. What is this right here?
That's Coral Gables Waterway.
Coral Gable Waterway. You can actually, I have a picture of that. You can sail your boat right up in there. So the big tourist ships dock out here somewhere.
Yeah, they jug Government Cut, which is Port of Miami.
Port Miami. So yeah, so they'll be able just to take advantage of the terminals that exist right here.
Get right from the airport to the boat.
There are some benefits. Obviously, if you throw storm surge on top of this, you got some you know, the problems just get even worse. But indeed, if 3 feet of sea level rise, and like I said, it's a conservative estimate by 2100, if that comes to pass, and that will come to pass if we don't do something about greenhouse gas burning, if we don't do something about levels of greenhouse gases in the atmosphere, then as I'll show you, there's such a very good relationship between temperature of the planet and sea level that this is going to happen. And this is going to make Miami a very difficult city to have for the future. This is the picture with 6 feet of sea level rise, which is sort of a 3-foot storm surge on top of 3 feet of sea level rise. Where's your house, Craig?
It's been moved farther inland.
Okay. It's a picture I stole from a friend of mine, Richard Alley. This just shows you, this is the, shows you the top of the coral reef from the last interglacial period. It's about 3 meters currently above sea level. This is how we know where sea level was in the past. Assuming there hasn't been tectonic uplift or depression, and in this area it's relatively stable. So this is the top of the coral reef 3 meters from 125,000 years ago or so. Here's sea level today. This is a coral that grows roughly 3 meters below the surface of the ocean, pretty predictable. And so sea level 125,000 years ago was up to here. And so that sort of scales it for you. Here's some apartment buildings. You will see these things sticking out of the water, the second, third floor, but the first floor, sort of like Venice, is underwater. And as this happens, if it happens slowly enough, I could certainly imagine a situation where we try to keep the infrastructure going and move people up, because certainly the Venetians have been doing this for quite a long period of time. They have a benefit in that Venice can actually be blocked off from the Mediterranean. There's no way that you're going to be able to block off Miami. Craig and I were talking about this the other day. It's either coral or it's sand, and both of those are very porous to water. And so if you built a wall circle around Miami, the water would just come underneath. And so unless you want to concrete over the entirety of Miami, and it probably is about 50% of the way there right now, then you're going to have some real trouble. I was just sort of Googling about Miami City of the Future, and I want to read this book, T.D. Allman's here, Miami City. This was published in 1987, I think. So Miami is indeed a city of the future. It just recently ranked number 9 city of the future. This is from April 18, 2011. And it's part because Miami is a large economic engine. It's certainly a large economic engine for Florida, but it's also a large economic engine for the country. It's a gateway to the southern hemisphere. It's one of the, and this is where a lot of growth is around the world. Brazil, other countries in Central and South America, their economies are booming, and a lot of that is tied back to Miami. So it is indeed, I think over the next 10, 20, 30, 40, 50 years, Miami is you want to look for a job, it's a good place. It's growth there is going to be large. Question is what happens after that? The area has been inhabited for around 10,000 years. Miami was incorporated as a city in 1896 with about 300 residents. I was learning a little about Miami's population today is 5.5 million. So in less than 100 years, or roughly 100 years, Miami went from 300 to 5.5 million. The reason why I tell you this is that 100 years into the future, will there be a Miami? So will Miami be this sort of bell curve of population? Will it go from 300 to 5, 6, 7 million and then back down? This is, I think, a really interesting sociological question. It's also a really interesting ethical question. Is this something that we want to do? Miami's the youngest major city in the U.S., and it's the old concept, last in, first out. Is that indeed going to play out? Miami will have lasted if we don't do anything. If we don't do anything about greenhouse gas levels in the atmosphere, Miami will have lasted around 200 to 250 years as a city. So there's and I don't know how to candy coat that. That is a fact. So, as I said, for the foreseeable future, Miami's future is bright, 10 to 20 years or so. For the long term, 100 years or more, Miami really has no future if nothing is done about greenhouse gases. And if nothing is done about greenhouse gases is the key. Heart of the issue, I think there's two hearts of the issue. One of them is whether or not 100 years down the road is of interest. And this is really difficult. It's hard to get people's attention for 100 years down the road. But something like sea level rise, which is like a freight train that's left a station that has momentum to it, it's really difficult to stop. It's not as if we can go 99 years and then say, oh, shit. Oh, excuse me. Shouldn't say that. Oh, poo-poo. We need to do something about this. That's not the way the system works. You have to have that 10, 50, 100-year vision if you're going to address this problem. And this is something that we've talked about in this conference, but that is a huge problem from a political point of view, from a sociological point of view, from an educational point of view. I think you can, certainly I think people who have studied the problem see this, even some who have studied the problem see it, struggle with, the concept of a century. But I think clearly, if you haven't studied the problem, if you're not educated about a problem, then 100 years is not going to be an issue to you. All right. How high will sea level go? I just want to point out, we've seen this before. This is, and we haven't actually seen one of these at this conference, I don't think. But this is CO2 levels in the atmosphere going from 0 to 350,000 years ago. It now goes 850,000 years in the past, but you just get the exact same picture. CO2 is bounded around 280 and 180 parts per million over the last million years, which is a very interesting thing in itself. Why does that happen? It is now, who was it talking earlier this week? 392, I think, is where we're at. And as I've pointed out before, that's a record. That's a record. That's a recent record. It's not a long-term record. But it's important to note that we are way out of bounds of normal variability here. This is another thing that people will ask about. Well, hasn't CO2 level been higher in the past? Yes, it has been higher in the past. But certainly over the last million years, and over the last million years is sort of a good baseline for us to consider, CO2 has not been anywhere near this high. And there's some very simple physics here. When the Earth is warmer, there's less land ice. There's less sea ice as well, but the land ice melts, and that contributes to sea level rise. And also you get, as ocean warms up, it rises. And so you end up with a very, very good relationship on our planet between warmth and sea level rise. It's largely linear over long time scales. I'll show you this in a second. But on shorter time scales, it can have exponential parts and slower parts. This is sea level rise from Greenland using the paleo record, using the record of the past, looking at different temperatures on a planetary scale. So here's today, which is called as 0. Here's the modern sea level. If you look at the last interglacial period, a period we call 5E, I apologize for that, roughly 5 meters higher sea level, and I'm sorry, this is sea level was about roughly 4 or 5 meters higher, and temperatures in this part of the world were roughly 5 degrees Celsius higher. There are even more warm interglacial periods as you go into the past, 11 being one of them. This is roughly 400,000 years ago, and it had an even higher sea level, and temperature indeed looked even higher. If you go back into the past, when temperatures were colder during glacial periods, water was taken out of the ocean to make land ice, and so sea level drops. And so you can sea level dropping 2, 3, 4 meters as you go back into the past. This shows you that particularly as you get into the warming part, there's a very strong suggestion that it's nonlinear. That indeed, if you go up 1 degree in temperature, you won't get 1 meter, and 2 meters, or 2 degrees, 2 meters. That probably these lubrication things that have the ice dynamical processes, we call them, will indeed play a large role, and you'll get some acceleration of sea level rise. It was mentioned before, the Arctic amplification of warmth. I think Jennifer mentioned recently it's been about a 2 degree amplification. I think you all know why this occurs. As you lose snow cover, as you lose ice cover, sun's energy can be absorbed, and so you get an amplification. Historically, that amplification is somewhere in the neighborhood of 3. So if you look at the paleo record, the 2 that we are seeing recently is actually on the low side, and that probably, if anything, the Arctic will begin to warm up even faster than the rest of the globe over the next 10, 20, 100 years or so. Just want to point out that sea level, while it may be level, it's certainly not, it doesn't stay the same. I mean, we live on a very dynamic planet. We tend to think of sea level just being there. This is a difficult concept for people to digest. When I give public talks, the idea that sea level could have been hundreds of feet lower and 10, 20, 100 feet higher, people just sort of shake their heads and go, how can that possibly be? Indeed, if you look into the past, this is the last interglacial period. Here's today, going back in time. Sea level was about 5 to 8 meters higher than present. It's about 2 meters here. It's about the same here. This is the stage 11 I was talking about 20 meters. So multiply these roughly by 3 to go from meters to feet, and you can sort of see that there are certainly, there have been times when sea level has been much higher than it is today. Change. The last time there was this much greenhouse gas in the atmosphere, this is an interesting question. What did sea level look like? The last time we think was roughly about 3 million years ago, when we had about 350 to 400 parts per million CO2 in the atmosphere. The Arctic was about 30 degrees Fahrenheit warmer than it is today. There were trees growing right up to the highest or the most northern parts of Canada. Some of those are still available. We can dig them out. Because that area is cooled off and you don't get a whole lot of decay, we can dig trees out of that area. Certainly less land ice, certainly less sea ice. At that time, sea level was about 20 to 25 meters higher, and we have probably 50 to 60 estimates around the world, ranging from 15 to 30, and we try to take out those areas that are tectonically active. And without putting those in there, you get a number that's pretty consistently around 20 to 25 meters. So that's roughly in the neighborhood of 60-something feet higher. This is another way to look at it. This is sea level on this axis and temperature on this axis, global mean temperature. Global mean temperature today is around 15 degrees. Sea level is sitting here at what we call 0. During the last glacial maximum, about 20,000 years ago, when the big ice sheets covered North America, sea level was around 125 meters, so in the neighborhood of 400 feet lower than today. That's how much water was taken out of the ocean and piled up on land. Same happens when you go warmer. The last interglacial period point plots here. The Pliocene, as we talked about in a moment, plots here. That's about 25 meters higher. If you go back further in time to prior to the Antarctic ice sheet, prior to the Greenland ice sheet, a time when the Earth was considerably warmer, sea level was around 70 meters higher. So in other words, if you took all the ice off of Antarctica, you took all the ice off of Greenland, if you warmed the planet up to that point, then sea level will be in the neighborhood of, what's 300 feet, 70 meters is roughly 300 feet higher than today. That's about how high it gets on the planet. It can't get a whole lot higher because there's not that much more land ice to take away. You can warm the oceans up and they will go up a little bit more, but that's roughly the max. I should point out. So this is the IPCC forecast, and the sea level rise number that they give is so small that the dot looks like it's 0. It's not. It's slightly elevated above the line. Even if you put 1 meter on here, that 1 meter, that dot's not going to move very much. Right? So you can see just how out of whack, if you will, what we're seeing today in terms of our estimates is with the long-term history of the planet. And there's really no reason not to think that with this kind of warming, we're not going to go to here eventually. And the word eventually is important because how long is that going to take? And I don't think we're going to sit back idly. Obviously, we're too smart to do that. I think we're going to find ways to try to deal with this problem. The question is how rapidly we do that. Change. This is just another way to look at this. This is in the context of CO2 levels. If you look at CO2 in the context of CO2 levels, this is the IPCC last estimate will be around 800 parts per million, and they give a sea level rise, which is this red line right here, of roughly, half a meter, something like that. Let's call it a meter. These dots are what we see in the paleo record. So you see that the sea level rise part is, with much less CO2 in the atmosphere, you get even more sea level rise. And if you really pump the CO2 up in the atmosphere, which we could do this by burning all the coal, this is sort of the level that things end up at. So the Earth does teach us a lot of interesting lessons. So what does 65 feet of sea level rise look like? I think I might have showed you guys these last year, but I thought with some new folks here and the streaming, we have time to revisit this. This is, Google Earth is a wonderful thing. You can go in and plug in sea level for your area, and if the right elevation maps are in there with enough detail, you can see some pretty interesting things. This is what I focused in on. The Netherlands, because they're fighting away at sea level here, so they're gone. We don't have anybody here from that area. 65 feet. This is Delaware, and here we have with Miami. It was last in, first out. With Delaware was our first state, and so Delaware may be first in, first out. If indeed we don't do anything about this, sea level rises to the point where the past tells us it will, then Delaware won't be around. They may still have their senators, but they won't have a state. So. This is what Florida looks like, by the way, in Louisiana. So the Gulf Coast is the coast that has the least slope to it, and so indeed, if you look at, you can find beach lines. If you go into some of here, you can find beach lines at those elevations if you look into the past. You look at the Pliocene, the 3 million years ago beach lines. And you really will be able to, this now gets really interesting because, Orlando's still there, and so, while your cruise ships aren't going to be happening, Craig, the Disney line is really going to be making out like a bandit. Yeah.
But the board's gone.
But the board's, yeah.
It just sail up to the castle. Did you do that in Google Earth?
Somebody else did this in Google Earth, and I took them from the web. But you can do it in Google Earth. This is what Bangladesh looks like. So it's not just obviously a U.S. question. I show this because it's interesting. This is the boundary of Bangladesh. And it's almost as if somebody said, okay, we're just going to figure out where the Pliocene sea level rise is, and That's where we'll put Bangladesh. Our military is very concerned about this. They've spent quite a bit of time and quite a bit of money looking at climate refugee issues because people aren't going to move from point A to point B easily. We've divided up the world into countries, and as you know, these are artificial boundaries that we create, and climate doesn't really care, and sea level rise doesn't really care what those boundaries look like, and so there's going to be some interesting issues in the future. A couple of other places I want to point out here. This is Oakland. So the Oakland International Airport. San Francisco, this is just showing you, particularly on the West Coast where you have much more slope, you're much less susceptible. As Portland actually is in fairly good shape, even with a relatively high sea level rise. I show you this because here in Colorado we don't like the Oakland Raiders, and so the Oakland Alameda County Stadium is well underwater.
But you stay at Berkeley.
We do. Interestingly, the Great Basin of California would be underwater, so we would be going. You'd look more like the Baja of Mexico, where you have these sort of island chains poking around down there. Who knows?
Yeah, you're assuming no change in subduction or rising of the landmass?
I don't think, no, yeah, this does not assume any tectonic uplift over that time. In over 1,000 years, I forgot what is the tectonic uplift on the West Coast? You know, it's a couple of millimeters a year, so it'd be a fight. I don't know that this is going up that fast in there. Okay, we'll switch gears here and talk a little bit about permafrost, clathrates, and methane. It is known that there's a lot more carbon in permafrost and in clathrates than in all fossil fuels. Just a little definitional thing here. Soils in cold regions tend to accumulate carbon, and that's because when photosynthesis happens in the summertime, you get accumulation of carbon, but the wintertime, it's too cold for respiration to occur to the same degree. And so cold regions tend to accumulate carbon in soils. And we've had cold regions in the Arctic for well over 13,000 years or so. Methane clathrates are, and I've talked about this sometime in the past, but methane clathrates are an interesting chemical phenomenon in which when you have decay with oxygen around will go to CO2. Decay with that oxygen around goes to methane. And methane decay in ocean sediments, if it's cold enough and if there's enough ocean pressure on top, then the methane gets trapped in a cage of ice crystals. So the H2O bits make a nice cage, and some molecules fit inside of there. They're not so big that they don't fit inside the cage, but they're also not so small they can't escape. And methane is one of those molecules. And so ice can form these, what we call methane clathrates. And if you Google methane clathrates, you can see some really cool things where people bring these ocean sediment cores up, and then for chuckles, they light them on fire. And so it's ice burning away there. You know. Scientists are really grown-up kids, let's face it. Actually, there's also some really neat videos. As permafrost warms up, some of that goes to CO2 and some of that goes to methane, and the ratio there turns out to be really interesting and very important for climate change. But methane actually accumulate underneath ice on lakes, and you can go out, and there are videos where folks are going out and you walk across the lake. It's thick enough you can walk on the ice. You see where the bubble is under there. You drill into it and then you light it, and you get this big burst of flames coming out of the lake. This is, yet again, you know, scientists being quality people. It's known, as I said, the polar regions are warming 3 times faster than the global average. It's a very good bet that at some point the polar carbon will be released to the atmosphere as CO2 and methane. And this is a very large positive feedback on the current warming. We're taking fossil fuels out of the ground, which normally, without us around, would leak out to the atmosphere on or weather on a very slow time scale. We've accelerated the the removal of oil, natural gas, and coal from the surface of the Earth by many, many times. That warming is going to trigger this stuff being released, which will then amplify the warming. There's really not too much that we can say that would be bad with that logic. The question is how fast this stuff comes out. And this has been something in the news quite a bit lately. There's a couple of stories out of Russia where they've seen large amounts of methane bubbling up out of sediments in Arctic oceans, and the Arctic oceans are warming, as Jennifer just talked about. And remember that cage of ice depends on both cold and pressure. And so as the bottom waters warm up, the ability of these clathrates to stay stable decreases, and so you start to get release of this stuff. So the speculation is how will the polar carbon be released? And will it be released rapidly and catastrophically, or will it be released slowly over time? And this is a question that we're beginning to look at. And just showing you, this just shows you methane over time. This is now going from today back 800,000 years ago. This one up top is methane. Methane's been bouncing around historically from about 700 parts per billion down to around 300 parts per billion. And it can go up very rapidly. Methane is tied to the hydrologic cycle, so when it rains you make swamps, and when you make swamps you make methane. So it can go up and down quite fast. And so you see there's quite a bit of jaggediness to this. Note the scale of the jaggediness. This goes from, say, let's be generous, 300 to 700, so 400 parts per billion. Methane today is 1,800 parts per billion, which isn't even on the screen. It's up in the, I don't know what's above us. It's up in the next floor somewhere. So what we've done to the methane cycle is really large compared to what we've done to CO2. But there's a couple of good lessons in here. One is that while this stuff bounces around, there is never a time when this methane shoots up to 1,800, 2,000 parts per billion, which it would if you took all of that permafrost, or if you had a methane clathrate release. If you dump that into the atmosphere in a short period of time, you would see large increases in methane in a short period of time. And there's nowhere in the last million years that we can see that this has occurred. So that gives us a scaling that even though we went into these warmer interglacial periods in the past, at none of those times did methane overshoot by large amounts. And nowhere it doesn't even get close to today's level. And to me what that says is that the methane release is likely going to be slower than what we think. That doesn't mean it's not going to come out, but it means it will likely be a slower release than something that would happen, say, in 50 years or 100 years or 20 years or something like that. So the paleo record is telling us something good at this point. There is a lot of permafrost. I pulled up a couple of slides here. Continuous permafrost in the darker purple all the way down to isolated. And you see most of this is in Russia, but there's quite a bit over here in Alaska and in Canada. This is just another way to look at it. I know I have two slides in here. Interestingly, methane has been going up, and we've talked about this in the past. Methane is a greenhouse gas that is tied primarily to some to energy, because it leaks out of pipelines, and it's lost from coal mines in particular when we go mining. But it's mostly, from an anthropogenic point of view, produced by cattle belching. It's produced by rice cultivation, crops that have their feet in the mud that allow the methane from the mud to make it up into the atmosphere through the stalk of the plant. So from about 1980 or so, it was rising, and again, we forget about scale here, but it flattened out for quite a while, and there was a lot of debate about why it flattened out. Was that because of something that we were missing in the methane cycle? Certainly it's because of something we're missing in methane, because we couldn't really explain it very well. But it's important to note that methane's going back up again. And, well, yeah, Matt, we'll talk about that.
Your different lines and labels there.
Oh, I'm sorry. This is, I just grabbed this slide. All of these are NOAA observation sites around the world. Barrow, Alaska, Azores, Alert Island, Cape Grim, Mauna Loa, Niwot Ridge in the middle of the U.S., Samoa, etc. So This is a selection from sites around the world showing this is a global phenomenon, that indeed coming up, plateauing for a while, and then methane is back on the rise. So the question is, why is methane back on the rise? Is that a sign that permafrost, clathrates, etc., are beginning to decay and starting this process of feeding back on the warming that we're seeing from anthropogenic causes? Interestingly, the answer is probably no. It's not permafrost for a couple of reasons. One is we also measure something called the carbon-13 ratio of this stuff. And just, you know, I don't need to know much about this, but the anaerobic, the bacterial it produces, the cattle, rice, cultivation, etc., has a very low value of this carbon-13, carbon-12 ratio. Fossil fuel burning has a much higher one. So what this tells us is that, again, flat, things weren't happening much in the methane situation. And then, beginning in the last few years, this value has begun to drop and drop precipitously. What that tells us is that this rise in methane is anaerobic. That is, it's swamps, it's wetlands, it's cattle, it's things like that. But that includes permafrost. So I'm going to skip that. How would we know it's permafrost over, say, rice cultivation in other parts of the world? Unfortunately, we measure around the world. We measure at many places around the world. And if it's coming out of high latitudes in the Arctic, we will see a larger increase in the northern hemisphere, and certainly a larger increase in the Arctic region than you would see in the southern hemisphere. If that methane is coming out in the tropics by more rice cultivation, and indeed that's where population growth is, then you would see what we call the interhemispheric gradient, the difference between the north and the south not changing very much. And indeed, this is an update from a paper that Ed Gulikenki and I were on, looking at, this is the interhemispheric gradient. And what you see is that this is the northern hemisphere minus the southern hemisphere. There is more sources in the northern hemisphere because of human beings, but the gradient hasn't been changing. If indeed we were looking at lots of permafrost methane being produced, these numbers would be ratcheting up to here. And we're not seeing that. By the way, you can see the impact of the former Soviet Union. When the Soviet Union collapsed, the interhemispheric gradient changed quite a bit. And the reason for that was the Russians have lots of natural gas, but they had really lousy systems for getting it out of the ground and distributing it. They were leaky as can be. And when the Soviet Union collapsed and a lot of that gas extraction stopped, the interhemispheric gradient dropped precipitously because Russia's obviously in the far northern latitudes. It hasn't gone back up, even though Russian gas has gone back up, because other companies have come in and rebuilt pipelines, and so they're much more efficient. So you can actually see human impacts on this. So the bottom line here is that while we know that this stuff is going to come out, we haven't seen evidence of that happening yet. But stay tuned. This might indeed, it eventually will happen. I'm going to go through this pretty quickly. There have been times in the past when we think these methane clathrates, these large concentrations of methane ices at the bottom of the ocean, have indeed catastrophically gone up into the atmosphere. The last, and one of the biggest times is something called the Paleocene-Eocene thermal maximum. I'll show you what that's a big mouthful, but basically there have been times in the past when the climate of the planet has gone up very rapidly in a short period of time because of the release of this stuff. They are rare events, however, and how rare you can sort of see on here. This is the Paleocene-Eocene thermal maximum. This is a very sharp warming. And so I'll back up. This is the temperature of the planet as measured by one of the proxies we use, going from present back in time. A couple of things you notice on this is the planet has been cooling off. So the Antarctic ice sheets didn't really start until back around here when the Earth had cooled off enough that you start to get ice sheets. But notice that these spikes are pretty rare. As a matter of fact, there's only a couple on there that we think are related to these things. So while we're nervous about these methane ices in the Arctic Ocean, we're nervous that they exist around the world. And as I said, there's more of this stuff carbon-wise than there is all coal, oil, and natural gas. So huge amount of this stuff. The Earth is telling us that, that this is not something that happens very often. When it does happen, it's a mess. I mean, there's no doubt about that. Globally, temperatures go up. High latitude surface waters go up even more. Bottom waters of the ocean go up 4 or 5 degrees, which is huge. Huge warming of ocean, of tropical waters. Even the tropics warm up, and today the tropics aren't warming that much because they're already pretty doggone warm. A whole bunch of things happened at the PETM. Sea level rise rose to thermal expansion. The ocean deep circulation actually reversed at that time. The ocean acidified, obviously, in a very major way, because suddenly you had methane that goes in the atmosphere that is oxidized to CO2. And we talked about ocean acidification before, but huge acidification of the ocean, which led to a mass extinction of benthic foraminifera. This allowed mammals to spread profusely. We're not 100% sure why that occurred, but probably a good thing for us. Major mammalian orders, including horses and primates, appeared and spread across the globe after that time. So this is, it is interesting when you get these large climate changes, ecosystems change. And we heard this earlier in the week that, you know, today we are causing extinction of species, but other species pop in. And so, but when we see major changes of life on the planet, it tends to occur when you get these major climatic events, and this is just one of them, showing that there's huge things that happened at that time. I'm not going to go there. So we have a half an hour. We can either do Q&A, or we can spend some time talking about nuclear energy. What do you want to do? Both. Both? Okay.
Can I ask a question about where we are right now?
Yeah.
I know I get a lot of questions from my viewers in Cleveland about they're afraid. There's a fear factor in this.
Yes.
They think this is a cataclysmic ending to life as we know it in the next 50, 100 years.
Mm-hmm.
And I think there's a reassurance in seeing these things that, you know, this has happened before. Not necessarily does this mean that we're in this, but I think one thing that I try and really stress to my viewers is that, you know, yes, things are going to be changing. Change isn't always bad, but we just have to deal with it at this point. Why is there such a fear factor thrown into climate change and global warming? Those two topics just freak people out, and why is there that fear factor?
Well, I honestly, I don't know the full answer to that question. I can give you some speculation. I think people in general are nervous about change, and there is indeed cost to change. You know, let's pick on Miami for a moment here. You're welcome, Craig. You know, okay, so we lose Miami. Right? That's, you know, part of the game. Right? But there's a cost to that, because those folks have got to go somewhere. The economic engine that is Miami has to be reestablished someplace else. You know, this is not going to be a cheap thing to deal with. And I think that people are nervous about that, you know, how much is this going to cost? I also think they're just nervous about change in general. You know, as humans, we kind of get into this odd mode where we like things to be predictable and we like things to keep going on the way they always have, and change we don't like that much. I'm sure you get, you know, you get it as weather forecasters and as on-camera folks all the time, that, you know, it's, people are probably much happier when they got a forecast that's, you know, nice and maybe changes on the slow side. But when you get like a boom kind of change, that sends people off into a different mental state.
Well, how do you feel about the tone, the overall, how do you feel about the tone, the overall tone when reports are given, whether it's media or whether it's, you know, just people in general trying to interpret things themselves, the overall tone that is given to the general public about, you know, climate change and what's happening, what could happen? What are your feelings on that?
Honestly, I think it is overblown, and it can be overblown. you know, I've been very surprised many times. I've had people come up to me on a number of occasions and tell me that, you know, we're going to wipe out life on the planet, or we're going to make the planet uninhabitable, or it's the end of the world. And I'm not sure where they get that message, but you're right, they're getting that message, and none of that's true. The Earth has been much warmer than today. Here's CO2 levels, for example, in the atmosphere in the past. Going back, you know, here's 1,000 parts per million, probably about where we're headed. Yeah, you got to go back 30 million years to get to that point, but you know, there was life on the planet, lots of life on the planet 30 million years ago. So I don't know. I agree that there tends to be a bit of a focus on the negative, as if the climate we have today was some something, you know, this is the way it ought to be. I don't. It's probably not the right word. Sacrosanct. What did I forget anyway? Who knows what I just said? You know, the climate that exists today is just the climate that exists today. It happens to be when humans industrialized and when we really spread out and covered the planet. But there's nothing unique or great about today's climate as opposed to a colder climate or a warmer climate in terms of the Earth. It may be in terms of us. You know, in terms of our ability to grow food, in terms of our ability to have the sophisticated societies we have, you know, there are bumps in the road when it comes to climate change, particularly with agriculture and things like that. But there's, you know, if you just want to take a step back and go, well, this is going to happen. Yes, it's going to happen. Are we going to dry up and blow away? No, we're not going to dry up and blow away. Mike, Matt.
A couple questions for you. Can you clarify the methane clathrate deal? Is that in the ocean or is that in the permafrost? And then also, can you speak a little bit about the current state of the climate models? I hear criticism of the models. And can you just speak to that? Where are they? Are they getting better? Where they're going? And it's interesting to me that some people are highly critical of those models and seem to expect perfection out of them when we don't even have perfection out of our synoptic scale models.
Yeah. The clathrate question, almost all clathrates are in the ocean. So the classical clathrates. There are some that you can find on land that are ices that are buried well down below the surface. But for the most part, we find them in the ocean. The vast majority of them are found in the ocean. The stuff that we're worried about in the Arctic is mostly frozen carbon in soils. In terms of the models, I agree. I think the models get beat up. The models are trying something very, very hard to do. They're trying to predict over the next 100 years what's going to happen, or 200 years what's going to happen, which is a very difficult thing to do because there's lots of feedbacks in the climate system in the first place. And human behavior is very difficult to throw into there in any kind of a meaningful way. What we do know about the models, and I think we've seen this from a comparison of paleoclimate and what the models predict, is that the models are consistently underestimating what the real world has done. And if anything, those models are conservative. So if you want to beat them up over the fact that they're conservative. They're not wildly off saying, you know, hellfire and brimstone on Thursday. You know, that's not going to happen. They are, you know, if anything, they're missing some of the feedbacks that help amplify the system that get us off into much warmer Arctic than we've seen, that we see in the past that the models have trouble predicting for the future.
Couldn't they also be underestimating some of those same feedbacks?
Yeah, there could be feedbacks that they're underestimating. So as we go through time, there may be negative feedbacks that creep into the system. I think, you know, what Jennifer talked about this morning is a good example of that, that, you know, if indeed colder air can come down and stay longer in the lower latitudes as a result of a warming Arctic, you know, that's an interesting feedback, and I'm not sure the climate models nailed that. Jennifer, do you know whether or not they see that in the models?
Well, we're just starting to look at some of the model output in terms of the kinds of things I talked about this morning, but in fact they are showing some increasing tendency for meridional flow, for blocking patterns and things like that. So I think there is some hope that the models are going to capture some of these more weather-related issues. And while I'm got the microphone here, I just wanted to mention the fact that you know, some people, you hear often that, you know, if we can't forecast the weather beyond a week, how in the world do we forecast, you know, out 100 years? Well, would you believe me if I said it's going to get warmer this summer? You know, they're really two completely different things. The forecast models that forecast the weather are very physically based. They're dynamical. They've got, you know, observations going into them, whereas climate type models are all about energy balance and, you know, very different questions. So I think that's an important thing that your viewers need to understand, because that's a common thing that you hear.
Yeah, the difference is, you know, trying to throw physics at the problem and see what happens. Whereas, you know, if you just throw physics at the next 10-day forecast, you won't do very well. You need that, you know, that past observations to help the skill.
Yeah, I guess my point was simply in terms of modeling. I understand the differences between near-time modeling and climate modeling, but my question was simply models in general. They're not always perfect, and yet there seems to be, on the skeptical side of the AGW issue, some deep criticism of the models, like, and just, oh, the models are terrible. They can't predict what we did in the past. How can they possibly, just in the climate sense, not in the meteorological sense, how can they possibly work in the future? I hear that.
Well, so, you know, let's say we didn't have the models. All we had was what we can see in the paleo record. The paleo record is pretty clear that if you have 400 parts per million of CO2 in the atmosphere, roughly, you're going to have meters and meters and meters of sea level, higher. That's pretty clear. You know, if anything, the models are saying, you know, we won't get there, and we won't get there nearly as fast. So, as I said, this is an important way to look at the models. They are conservative. So if you want to beat them up, you know, then you're really, you know, you're picking on the, you know, well, I don't know. I don't know how to finish that sentence in a clear and clean way. But, you know, the bottom line is that, yes, I mean, this is a very challenging thing to do, to model global climate and to get it right on timescales of human interest. But keep in mind that the models that we have right now, what they're telling us is much more conservative than what the past tells us. And so, if anything, things are going to be more interesting and warmer and all the other things that we know are going to happen than what the models predict.
And if I could just add one more thing to that, you know, the real world is like one model run. And there's a lot of interannual variability. There's a lot of randomness to the climate system. And so to expect a model to perfectly simulate what the real world has done is really a very unrealistic thing to ask it to do. But if you do force it with, you know, volcanic eruptions and the greenhouse gas increases and the land cover changes and things like that, they actually do an amazingly good job of simulating the general patterns of the atmosphere. But you cannot expect a model to totally reproduce the one simulation that the real world is.
There was, just real quickly, Dr. Jerry Meal came and talked to the Weather Channel, and what these climate models have been around for 30 years or so, and they're obviously getting better. But just the simple statement that if you take the amount of CO2 produced by humans out of the equation, you can't get the results that we are seeing actually from year to year as you average the global temperatures, you know.
Exactly.
And that's when it hit home to me, is like, well, yeah, and the whole thing that, yeah, I'm a meteorologist and I look at synoptic dynamic models and I know how wrong they can be, but it's a whole other, it's a heat balance thing. It's completely different. And once that was explained to me, you're like, yeah, it's kind of makes sense now. All the people, you know,
yeah,
meteorologists in general tend to be a little slower to get on because they're like, in my world, models have trouble and I see all sorts of weather extremes. So we've been slower to come around, but when those kind of things get explained to you, and even your talks at this conference, you kind of go, yeah, it's happening.
Yes.
A few months ago, there were stories out about giant methane bubbles coming up through the ocean in the Arctic.
Yeah.
Is that a sign of the methane clathrates being released?
Well, that's what I was trying to address here, that it's not clear how unusual that is. that this may be going on all the time. The atmosphere is telling us, and I didn't do, digging into the details there, but the atmosphere is telling us that if there, bless you, if there was lots of that happening, we'd see it in the atmosphere. And the atmosphere is telling us no. That yes, methane's going up again, but it's going up again because of what's happening in the tropics and not what's happening in the Arctic Ocean. So I think that yes, indeed, methane comes out of the Arctic Ocean, and methane comes out of lakes in frozen areas, and methane does come out of permafrost, and CO2 does come out of permafrost. But what the past tells us is, number one, it's very, very rare that we see this happen catastrophically. And number two, it's not happening right now, at least to the point where we can see it in the atmosphere. And in my world, if you can't see it, in the atmosphere, then it ain't happening yet. Now, I will say that there's no reason not to think this won't happen. The Arctic is warming up. You will get carbon release from the Arctic. There will be that feedback that happens at some point. Yeah.
I've had, going back to talking about viewers' perceptions and how we explain away the inconsistencies in the models, I've had some success in talking to people and saying, I go back to the LFM days, which most of you don't even remember, when if we got the next day close, we were pretty happy. And now we look at some of the GFS and European runs out 7 to 10 days, and these things develop these short waves or cut off lows. And when those 7 to 10 days pass, we look at it and we say, well, the low developed 200 or 300 miles east or west of what the model initially thought, but it did develop, and it didn't cut off, but it was there. And to me, that's a huge success. Now, your perceptible weather was different than it would have been had it been the exact outcome that the first model did. But the fact is, we knew that low was going to develop, and we knew it was going to have an impact. We don't know exactly what those impacts will be, and I think that puts it in a frame of reference for the viewer, that he has a little better, oh, okay, I see. You don't know exactly, what you're saying is there's going to be more methane in the atmosphere. You're not exactly sure what that impact will be, but that's something we're going to be looking for. And as we get closer, we'll have a better idea. That's just one way I've explained it away.
Well, that sort of triggers kind of a soapbox moment for me. We don't spend a whole lot of our money in a percentage way on either weather models or climate models, or weather observations for that matter. I mean, if you look at the number of observations that are out there, they're not, if we had more observations, you guys could make better forecasts. I think you know that. If more money was spent developing models, you could make better forecasts. And for some reason, we don't put, even though that's a huge impact on the economy, we don't put that kind of effort into it. The same problem exists in climate models. We spend it might seem like a large sum of money when you add it all up, but compared to the amount of money we have available in society to spend on things, we don't spend a whole lot of money at all looking at climate and looking at the future.
I tell people that our models are good enough now that we could get a much more accurate forecast if we had better data to put into it.
Yep. And if anything, we see the data decreasing. We see sites being cut back. We see this.
Yeah, hey, Jim. I've taught climate change in Huntsville, Alabama, where Rush Limbaugh is considered a bleeding heart liberal for a while. And there's a great graphic. It's from Stott et al. 2000. I'll pass this over to Matt if you want to see it. You've never seen it before. But it shows the model runs with and without carbon dioxide. And it also overlays the temperature of the planet since 1850. And it's a great answer to that skeptical question you get.
Yeah. Now, we've looked at that in past talks that I've given here, that if you take greenhouse gases out of the simplest models or the most complex models, the same thing happens. You can't get the warming after 1970 to happen. Without extra greenhouse gases, you just simply can't get that warming to happen. You know, all the other oscillations are there, all the other, the volcanoes are there, the sun is there, everything else is in there. But if the greenhouse gases aren't in there at the levels we have, you can't get the planet to warm up to the levels it's at right now. We have a few minutes?
Go nuclear.
We can't go nuclear in 7 minutes, I don't think. I'll give you a very quick synopsis on nuclear energy. How's that? Yeah. All right. Because this is something I hear about a lot. You know, what about nuclear energy? One of the interesting things about nuclear energy is that there's not as much fissionable material out there as one might think. When we were first looking at nuclear energy, we were talking about thousands of years of nuclear energy being around. Nuclear energy today in the industrialized world provides about 6% of our energy, which is about 20% of electricity. Electricity is only about 20% of our total energy consumption. And at the rate at which we are collecting and burning fissionable material, and it does indeed burn in that same sense, it goes from one form to another form. We've got maybe in the neighborhood of 50 to 150 years of fissionable material out there. And that's with nuclear energy providing only that 6%. If you put growth into the equation, 3% growth per year of energy needs, then if nuclear energy is just to hold its own in terms of 6%, then that lifetime goes from, say, 100 years, take an average number, down to maybe 50, 60 years or so. If you want to provide more and more of energy from nuclear, then obviously that number gets smaller and smaller. So if we went from 6% of our total energy nuclear to 10% or 12%, then all those numbers get cut in half. There are ways to stretch your nuclear budget, one of which is to reprocess nuclear. And maybe this is something we can get into in another conference. Reprocessing and breeding, making plutonium, which you can also burn then. There's some interesting weapons implications there. And right now we're very nervous, for example, about some countries around the world that are enriching uranium. When you enrich uranium, you can make an atom bomb. And atom bombs are bad. But when you have a reactor that can make plutonium, which is one of the ways to run a reactor, then you can make hydrogen bombs. And hydrogen bombs are really bad. So, military uses roughly half of the fissionable material today. So if you wanted to have more for nuclear energy for us, then you'd have to figure out a way to get it out of the nuclear, get it out of the military's hands. Reprocessing can also roughly increase by half. But indeed, that has interesting implications from a weapons standpoint. So when people ask me about nuclear energy, my response is, you know, if it was something that would last for thousands and thousands of years, I'd look at this differently than I do knowing that it's not something that's going to carry us a long way into the future. There are downsides. You know, obviously there's a weapon issue when it comes to reprocessing nuclear energy and making plutonium and making atom bombs and things like that. But there's also a waste issue. This stuff produces, you know, everything we do produces waste. Carbon dioxide is a waste. Nuclear energy is a waste. Turns out, or nuclear, the spent fuel rods and things like that are a waste. Turns out that you got to keep an eye on nuclear waste for a long time, thousands of years. It remains dangerous for thousands of years. It remains something that is not only poisonous, but if the wrong people got their hands on it, they could make a mess out of metropolitan areas with nuclear waste. So it's something you got to watch and maintain for a long period of time. What does that cost? There's a large cost associated with nuclear waste. Right now, it's not rolled into the price of nuclear energy production because we made a choice, or our lawmakers made a choice, to take that out. So what you buy, the electrons you buy from nuclear energy, are relatively cheap because we've chosen to take the waste disposal out. The same is true for fossil fuels. We don't consider the cost of climate change when we buy electricity. So the waste is externalized, to use the economic terminology. Personally, I see nothing, there's nothing fundamentally wrong with nuclear energy in the sense that, yes, indeed, it produces energy. To me, it really boils down to a cost-benefit analysis. How much is it going to cost you to deal with the waste, and how much benefit are you going to get out? And there's that you can look at the long term. You can look at it the short term too. There's, a lot of people argue that, this is a bridge. It's not a climate changing thing. It doesn't produce carbon dioxide. We can use it as a bridge to get from point A to point B. It is a short term bridge, though. And if we have time in a future Weather and Climate Summit here at Breckenridge, we can get into that.
So then what is the answer? What is the answer for a fuel source so we can lower our fossil fuel use? Solve the world's problems.
Nancy's asking what is the answer. Again, this is something we, I said I teach an entire semester of this starting next Tuesday. The only energy source that we have that has longevity and comes in large quantities is solar. And solar gives birth to a whole bunch of other things like photosynthesis to make biomass. It makes winds from, as you know, from the climate. It's the sun that really ends up driving the weather and climate system. It's really the sun when you boil it right down to it.
That was easy.
Yeah.
Let's do it. We need time to spare, I think.
Anything else?
Any other questions? We actually do have a minute and a half left.
Minute and a half. Yeah, my notes are yes and no. My notes are online. The University of Colorado has gone to a more internalized system where you can't get there unless you're a CU student. But I can certainly. I've posted them on a public website before, and you can get all those notes. But you can also come back and learn all about that. Huh? Back here at Breckenridge. You want to stand here for about 30 seconds?
No.
No? No.
That sounds great, Jim. Thank you very, very much.
Thank you.
Now, this draws us to an end. I just need to get a piece of paper here for a second of the 2012 Glenn Gerberg Weather and Climate Summit, and it's been a terrific one. Jim, your insights have been awesome today. Dr. Jennifer Francis, it's also Dr. Jim White. Dr. Jennifer Francis from Rutgers gave a wonderful presentation. And for those of you online viewers, we appreciate you watching throughout the week and really participating. It's the first year that we've tried this, and I think it's been an overwhelming success. Last night I mentioned at the dinner that we had over 1,000 unique viewers of the Weather and Climate Summit, and this has been terrific. So we invite you back next year. We will certainly publicize it a little bit more, so those of you who are just catching the tail end can participate next year. We also have the YouTube videos that will be posted over the next couple of days, so you can actually come into the YouTube channel and get access to every single presentation that happened out here in Breckenridge this year. So this has been terrific. I also want to acknowledge the fellow who produced the music. We had some positive comments about the music with the full screen banners and everything that with the schedule. And it's Canton Becker. He provided the music mix, and you can reach him at Canton, C-A-N-T-O-N, @gmail.com if you need any music mixed for any presentations that you'll be putting together anytime soon or in the future. I also want to acknowledge Image Audio Visuals. They're the folks that provided for this entire Weather and Climate Summit the cameras, the HD cameras that we're using, the pipe and drape that you saw behind us, and also a lot of the rear screen projection equipment that we used here. That's the first time that we've used rear screen projection equipment, and I think it was terrific. You don't get those shadows and all that sort of stuff on the screen, and it works much better for live streaming. So again, thank you all for coming. Again, this Weather and Climate Summit was really focused on bringing television meteorologists together with scientists so we can further the dialogue about what is being learned about climate science and also weather technology. We had a number of excellent weather and weather technology presentations earlier in the week. So with that, I will wrap it up and thank everybody for coming. Once again, the Glenn Gerberg Weather and Climate Summit is now over, and we appreciate all of you joining us. We'll see you back here again next year. Thank you very much.
Good job, my man.